This is a brief demonstration of a few of the most common types of digital filter used for transforming the spectrum of an audio signal. These two windows each contain a graph of amplitude over frequency, showing the possible range of frequencies from 0 Hz up to the Nyquist frequency of 22,050 Hz. The upper graph shows the spectrum shaping effect of a digital filter, with the central horizontal line indicating no change in amplitude, and anything above or below that center line indicating that the filter will impart a boost or reduction in amplitude at a given frequency. The lower graph shows the approximate spectrum of the sound in real time, which permits us to see the change caused by the filter, as well as hear it. Probably the most commonly used filter for audio is the low-pass filter. It has this name because it passes through the low frequencies and reduces the amplitude of the high frequencies. The most crucial parameter of a low-pass filter is the cutoff frequency, the frequency above which the content of the signal begins to be significantly attenuated. This filter here is set to have a cutoff frequency of 10,000 Hz, which is very high. It means that the frequencies that are attenuated by this filter will only be in the very top octave of our hearing range. I'm going to turn on some noise here. By changing the cutoff frequency, we can change the effect of the filter. Now, because white noise contains equal energy at all frequencies from 0 Hz up to the Nyquist frequency, it's often used as a good test of a filter's effect. Notice that if I raise the cutoff frequency to 20,000 Hz, we hear a slight increase in the hissiness of the sound in the very highest frequencies. But it's not an enormous change perceptually. Here we'll go back to 10,000 Hz. Now let's change the cutoff frequency to lower frequencies. Here's 5,000, 2,000, 1,000, 500, 200, and 100. Now, because we're less sensitive to very low frequencies, we have to turn up the volume a bit to hear this extremely low-pass filtered noise. But of course, the filter is not an absolute brick wall. It doesn't suddenly suppress all energy above the cutoff frequency, so we still hear some energy above the cutoff. But the cutoff is a good guideline for what we can expect the filter's effect to be. Now let's change the filter type to the opposite, a high-pass filter. This will pass high frequencies and attenuate low frequencies. Since the cutoff is 100 Hz, we're going to hear all of the frequencies above that. A high-pass filter is commonly used to filter out unwanted low rumbling noises, especially when the part of the signal we want to hear doesn't contain low frequencies itself, such as a violin or a flute or a female voice. Now, as we raise the cutoff frequency, the noise loses its full body and gets hissier. Now let's do that same thing to a sustained tone with a fundamental frequency of 440 Hz. We'll use a sawtooth waveform because it's rich in harmonics, somewhat like a violin tone. Notice how the tone is at first bright and buzzy because of the high frequency energy, but the low-pass filter can make it sound less bright, even making it sound rather dark and muffled. Of course, if we set the cutoff frequency very low, we're going to actually attenuate the sound almost entirely. So as a rule of thumb, a low-pass filter is used to make a sound darker or more muffled, or perhaps to remove some unwanted high-frequency noise that's in the signal. Now if we switch to a high-pass filter, we'll hear all the frequencies again, but as we raise the cutoff frequency, the lowest partials will be attenuated. The reduction of amplitude of the first partial doesn't completely change our perception of what the fundamental pitch is, but it does make the sound seem thinner and tinier. Now, it probably goes without saying, but I'll mention it anyway. If a sound doesn't have much energy at high frequencies to begin with, like this sine tone, then a low-pass filter might not have much effect. Notice that there's not much change for any of those settings, unless we make the cutoff frequency sufficiently low so that we actually hear some attenuation of the fundamental frequency. A bandpass filter is essentially a combination of a low pass and a high pass, leaving only a chosen band of frequencies to pass through, which is called the pass band. So when we're talking about a bandpass filter, we change the term cutoff frequency to center frequency in order to refer to the frequency at the center of the pass band. The width of the band will determine how drastic the filter's effect is. The term bandwidth has a specific definition. It's the range of frequencies beyond which the sound is attenuated by at least 3 decibels. So we might have, for example, a bandpass filter with a center frequency of 1000 Hz and a bandwidth of 500 Hz, which will leave a relatively narrow band of frequencies around the 1000 Hz. And it will reduce the amplitude of all of the frequencies outside of that 500 Hz range. Another term you'll hear used frequently in reference to bandpass filters is the Q. That's short for the quality factor, but everybody just says Q. The Q has a very specific definition. It's the center frequency divided by the bandwidth. So our filter with a center frequency of 1000 Hz and a bandwidth of 500 Hz has a Q value of 2. Or if you know a center frequency is 1000 Hz and you know the Q is 2, then you can calculate that its bandwidth is 500 Hz. By sweeping a bandpass filter over white noise, you can get a good sense of what different frequency regions sound like. If you narrow the bandwidth considerably by increasing the Q, in this case, the frequency divided by the Q will give us a bandwidth of only 100 Hz. You can even narrow the bandwidth to the noise to a point where everything but the center frequency is attenuated so much that the noise starts to have a recognizable pitch. Depending on the coefficients used in the difference equation of a bandpass filter, the filter might have not only an attenuating effect on frequencies outside the passband, it might also have a resonance effect on and around the center frequency. So bandpass filters can change the timbre of a sound quite dramatically. If I switch to a sawtooth wave, you can hear that I now have the ability to apply this narrow bandpass filter and emphasize particular harmonics of the tone. Now let's try applying these 3 filter types to a piece of recorded music. We'll start with a low-pass filter, with its cutoff frequency set so high as to have virtually no effect on the sound itself. I'll try the low-pass filter, then the high-pass filter, and the bandpass filter so that you can hear the different effects. I'll turn up the volume a bit so that they'll be more clearly audible. There are many types of audio filter, and we've seen three of the most common: low pass, high pass, and band pass. In a music production application, the user will often be presented a cascading series of high pass, band pass, and low pass filters with a helpful graphic interface that allows the user to control the cutoff or center frequency, the slope or Q of the filter, and the gain or attenuation of each filter. I'm going to play some music and adjust first a low pass or a high pass filter, a low pass filter, and then a band pass filter so that you can see the interface and hear the effects. This process is called equalization, or EQ for short, which allows the producer to get exactly the timbre of sound that he or she wants by adjusting a series of different filters.